Hello, I'm very happy to be here at JuliaCon, and I'm happy to meet so many people I've only known on GitHub. Okay, so a little bit of background. I'm a PhD student in economics at Princeton, and I have some coding experience in Stata, R, Python, and I started coding in Julia a year ago. And so I'm going to present a few packages I did, particularly last summer. So that aim for, especially for researchers in economics, but maybe they will interest some of you. All right, so economics, you need computer science for two things. The first kind of software that we do is computational economics, so it's a lot about a nonlinear solver, PDE. And so this kind of work is done in MATLAB on Python. And so the kind of work I come from is more data analysis, so a lot of data cleaning, but also statistical estimation. And so this is the part I'm going to talk about today. And so this part is usually done in Stata, which is a language a little bit like R for data analysis, but centered on data frames. And so you see that in computational economics, Julia has a lot of packages like jump, interpolation, and compicons that are particularly suited for computational economics. But there are relatively few packages for data analysis. There's data frames and GLM. And so what I started doing in my first project in Julia was a model to estimate models with high-dimensional categorical variables, which is the bread and butter of economists. All right, so I'll talk a little bit about the kind of model I'm going to estimate today. And so the basic idea is to, for instance, measure the impact of minimum wage on unemployment. Okay, so you have data on regions in different times. You have a minimum wage, you have unemployment, and you want to see the impact of one on the other. And so you might want to start with an OLS. But the thing with this OLS is you have confounding factors, right? So maybe some regions have, are like poorer region, have like higher unemployment and a higher minimum wage to begin with. And so you're not, beta is not measuring the causal impact of minimum wage on unemployment. And so what economists usually do is to absorb the confounding factors by fixed effects. And so, for instance, you may want to control for region on time-specific shocks. So the idea is, so by adding like this alpha I, you are going to concentrate on the within, you are going to look at one region and see how in this region unemployment changes when a minimum wage changes. So it allows it to, to remove all the between differences between different regions to concentrate on like what happens when the policy is implemented. For similar reasons, you want to capture time-specific shock by a gamma t. You might also want to interact this region-specific effect with aggregate shock like GDP. So for instance, in the second specification, you have an alpha I that is a county region-specific shock, gamma t, which is a time-specific shock. And then you also control for the fact that different regions are exposed differently to aggregate GDP shock. And so the whole idea is beta is going to change in this specification, and the whole idea is to, when you add like sufficiently fixed effects, hopefully beta will capture only the causal impact of changing minimum wage on unemployment. Last thing that you can do is this interacted fixed effect model. And so instead of, so you want to control by like a factor structure. So you see like the sum of lambda I, ft. And this allows to control for like different region exposure to unknown aggregate shocks. And the idea is like you're going to estimate what this lambda I and this ft are during the estimation process. And so these are all like linear model except the last one. And so these are fairly straightforward to estimate, except that we have a lot of variables. So for instance, alpha I corresponds to like n different regressors. One regressor is like one dummy for each different region. And so it's actually hard to estimate this kind of model, and so what I did in Julia is like to facilitate the estimation of these 3 different models. So I'll talk a little bit about the math behind this optimization. So denote X the matrix of regressors, and basically we want to find a beta with like the usual OLS formula. So the difficulty is like we cannot form X prime X, because even if X is a sparse matrix, X prime X might not be a sparse matrix, and then you cannot form it, and we cannot, of course, invert it. So we need to do something. We need to use like sparse least squares, and so there are a lot of ways to do it, but like the more intuitive way to explain what we're doing is the basic idea is like we want to project Y on the complement of X, and the way to do it is to decompose X into different projections and iteratively project on complements on these projectors, and hopefully at the end we'll obtain a residual that is orthogonal to all the elements of X. So if you find a sequence of projectors that compose P, if you iterate them enough, then you'll end up on something that is orthogonal to everything. So that's the basic idea. And so different methods just vary in terms of what kind of projector you choose. So this is like just the geometrical idea of like projecting, and at the end you will end up on X, which might be slow if you don't use your projector in a nice way. So you can project by columns. So this is a very intuitive stuff. So the idea is we have a lot of regressors. We just project with respect to one regressor at a time on which cycle. And so at the end of the day, we're sure to converge, but the conversions can be actually arbitrarily slow, so it's not a good idea. But this is the kind of conversion that is done in a package in R that wants to aim the same problem. That want to solve the same problem. We can project by rows. This is the usual Adama method. You can also use rows randomly. So you take a projector random. You take a random row, and then you take the residual with respect to this row, and then you iterate on the rows. But the best way, the best way, at least when I try, is to use something like conjugate gradient descent. And the idea is like the projectors are a little bit more complicated. It's not like columns and rows, but they are chosen efficiently. And so you actually converge after a few steps. Another method to solve this kind of like large least square problems is to use factorization methods. So you have like suit sparse in C++. And so this computes for Lexi on QR factorization for sparse matrices. The issue with this kind of method is that it's very slow compared to iteration method, and it has a big memory issue. So even if X is sparse, nothing tells you that X prime X is going to be sparse, and that the factorization is going to be sparse, so it might not even work in your problem. Also, I really like the flexibility of iteration methods, because I don't even have to form the X matrix. Like all the conjugate gradient descent only work by defining operations. So for instance, you have to define multiplying by a matrix, multiplying by its transposing. And then it's like duck typing. So if you define these two operators, you don't need to define the matrix. So you can actually run the algorithm. So I've talked a little bit to Tim Davies that wrote the suit sparse in C++, and he told me that for some problems, these factorization are better. So I don't think I've encountered such cases in economics, but I'm curious. I'm curious to learn about problems where it's better. All right, so now we're interested in standard errors of the estimates too. And so now the trick is, for instance, suppose we're interested in the estimate of standard errors for just a subset of the regressors, like X, and D is like this high dimensional matrix with all the other regressors. So we just observe that we can take the orthogonal projection with respect to everything in D, and then we obtain the second system that you see. And the nice thing is that in this reduced system, the estimate for beta and the standard error are the same. So if you regress the partial y and the partial x, you get the same beta estimates that you will obtain in the first specification with the right standard errors for beta. Okay, so that's the way to obtain standard errors for a subset of estimates in these large-scale models. Okay, I'll talk a little bit about sparse nonlinear system. So here, instead of doing linear least square, we want to solve a nonlinear least square issues. And the very simple idea is just to approximate to a nonlinear function by a linear function around a given point that you are. And then you minimize this function, you find the betas that minimize this function, and then you update. Okay, so this is like the Gauss-Newton step. And so the nice thing is you see that in the step 2, it's just OLS. Okay, so nonlinear least square is just like a sequence of linear least square problems. And so since we know how to solve linear least square, we know how to solve nonlinear least squares, even with like huge matrices. In truth, like a Newton method is not the best method, so there are two very good methods to do that. So one is like dampened Gauss-Newton with like this mu, and the other is to take a linear combination of Gauss-Newton and gradient step. Okay, so basically in the package to solve this nonlinear least square problems, you have the choice between Levenberg and Marquardt or dogleg method, and then both like and then you can also choose your linear least square solver. And so the two things are independently, are completely independent. Okay, so you have the choice of optimization on the one hand, and the choice of a least square solver on the other hand. It's a little bit like Ceres solver that is used in Google. So I don't know, who knows why they use nonlinear least square optimization, but apparently they use it a lot. So there is a Ceres solver for C++, and so basically this is like a Julia equivalent. And so a nice thing about this least squares optim package is like it's very memory efficient. So in this problem, generally the gradient matrix is very big, and so everything is made to avoid allocations within each iteration. There is even like a nice thing that you can do if you use like sparse factorization. You can just compute the symbolic factorization at the beginning, and then you just need to update the symbolic factorization numerically, but you don't have to recompute the whole factorization at every step. All right, so I'll go. I'll present the packages I'll be a little bit more specific about the packages I've written. So least squares optim is just for backend. It's just like to solve this general R of X optimization issue. And there are two high-level packages that use this package as a backend. Okay, so these packages are just two ways to adjust two instantiations of like nonlinear least squares problems. And in every case, all the hard work is done by least squares optim. But then like these are high-level packages that you may want to use in an easier way. So the first is fixed effect model, and so the fixed effect model are the one with are linear least squares with like a lot of regresses, and like sparse factor models is non-linear in the sense of you have this sum of lambda I ft, and you want to estimate both the lambda I and the ft. And so this is the speed of fixed effect models compared to two different packages, one in Stata and one in R, to solve the kind of issues, the kind of problems that we're facing in economics. So there are like 10 million observations. So it happens actually a lot if you use like tax returns data, administrative data, and you want to run like a fixed effect at the family level, individual level, or even like zip code level, stuff like that. And so very quickly, you see that in Stata, because the language is not very fast, and you need at every step of the iteration to multiply by these sparse matrices, which is actually a for loop, Stata becomes very slow as soon as you add like fixed effects. R is very slow, even in simple OLS. So actually, that's the thing I discovered. But R is it's actually, even if you do just simple OLS, it takes like 20 seconds just to set up the problem and do on inverting a matrix. So that's surprising. And then it's so the core of the package in R, like the loop I was talking about, is coded in C. And so even if it's coded in C, you see that it's actually way slower than Julia. So yeah, Julia is in blue, so it's actually very fast in any case. So I'm pretty happy that I've been able to do something that efficient in Julia. The main thing is really that the core of the algorithm is just a for loop, and for loop are typically very easy in Julia, so that explains these differences in timing. There is also, I think my algorithm is a little bit better than the algorithm in R, but I don't think that you can really, it explains the difference that you see in these timings. All right, so I'll talk a little bit about design choices. So because I come from Stata, and a lot of people that do data analysis in Julia actually come from R. I have like different ideas on what regression command should look like, and so I'll try to discuss them a little bit. So that's an occasion to explain my views. So the nice things about Stata is typically when you estimate a model, you also specify the kind of standard errors you want to compute. If you're familiar with R, generally you're going to use an estimation method and then you're going to use another package like VCOV or another package that computes the standard errors that you prefer. And you're going to hope that the two packages are compatible. That is, that the result output by the first model is actually acceptable as an argument for your standard errors package. So in Stata, both are done by the same functions, and so I think it's way better. So it's a little bit more work for the developer in the sense that there is still a package called VCOV, but you have to call it within your function rather than asking the user to do it afterwards. And actually, sometimes you really need to do the same, both at the same time. So it's a hedge example, but it's a particularly important one. So you see here, like I compute the standard errors with VCOV clusters, so it's like cluster standard errors. And so generally what you want to do is, the county is going to be an important variable. So I'm not going to explain what cluster standard errors are, but basically you need a county variable. And so suppose county is missing for some observations, you want to throw these observations from the model you estimate, okay? And so that's something you cannot do if you estimate the model in the first step and then pass the result to a different package. So basically at the beginning of the reg functions, what I do is I remove all the observations where variables are missing in the model, in the formula, or variables are missing to compute standard errors. And so yeah, another good thing about like computing standard errors is directly when the result prints, you directly get the t-stat you're interested in. And so computing correct standard errors is incredibly important in economics. And so my sense is that in R there's a little bit of like afterthoughts, and so I think it's important, at least for the audience that I'm looking for with this command, is to compute standard errors at the same time that I compute the estimates. All right, another difference with a typical estimation result in R is that R functions typically return a design matrix. So basically, you start from a data frame, you call the fit command, and then the command is going to form a matrix from your data frame. It's going to compute the factorization for x prime x, and it's going to put a vector of residuals, a vector of predicted values, basically a lot of information, and in case you need it later. The big issue with that is that suppose you have a data frame that is like 20% of your RAM, and then you output a result with all this information. It's going to take as much space as the initial data frame you started with, and so you can estimate like 4 different models, and then you're out of RAM. And so that's something that is really surprising to me. Like I started from Stata, and in Stata, like basically the return of an estimation command is like super minimalistic. So you just have the vector of estimates, the covariance matrix, a vector of Boolean for rows used in the estimation, and a vector of statistics, like a degree of freedom, etc., like a little dictionary. And that's enough, actually, because if you want to predict, you can predict if you... so for instance, in my package, there's still a predict method, and you just need to pass the original data frame. and you predict. So you use the return of the comments, you use the data frame, and then you can actually form the predicted value, you can form the residual, and stuff like that. So it's actually enough to do a lot of stuff that we generally do after estimating models. It's enough to return a very minimalistic models. And so, you know, the difference is actually very important. So I've read, like, for instance, at Stack Overflow, people estimating like 5 different models in R on big data sets, and then they want to print these 5 different models in the same table, and they actually don't have space to keep it. They need to keep all the results so that they can use like their fancy table printing from regression results. And so they need to keep like the whole results just to pass them to a table that prints 3 coefficients, and so they lack memory to do it. So that's I mean that's an edge case, but that happens a lot if you're working with really like big data frames. So I really like minimalistic results, so I've chosen to have them returned by default. And if you want to save other stuff, like for instance the coefficient of fixed effects, the residuals, or the predicted value, you can do so with an option, but it's not the default. So this is basically what happens when you use the program. So you do reg. So reg is the name of the corresponding stata command. So you have like a y, so sales. Then you have this symbol. Price is a regressor, and then like in this example, I have 2 high-dimensional categorical variables, state pooled. So it's like a pooled data array that enables to that specifies the state, and like year that specifies the year. And so basically, you see that I don't print the estimate for state pool and year pool, which is generally what you're not generally interested in them. You just put them in the regression to control for these omitted variables. And so you see the estimate, you see the correct standard errors. So here they are clustered by a state. And you actually directly see like the result there is a pretty printing with every information that you want. So that mimics a little bit like how Stata works on Python, I think. And I think like this kind of like result with directly the errors directly like is much better to work with compared to usual commands in R. I'm not I like R a lot, but I haven't met a lot of people that actually worked with Stata before, and I think Stata is actually has a terrific syntax, especially for these scan commands. So that's why I wanted to replicate this. Okay, so in conclusion, so I built like this least squares opt-in package to solve this least square problem. They can be linear or nonlinear, and I use them in two high-level packages. The first is like fixed effect model. That is like 90% of like what applied researchers do in economics. So it's actually so it also does instrumental variables. So I don't talk about it today, but it's a very big thing in economics. Clusters and errors, and so really it's a bread and butter of like applied research in economics. So hopefully it will allow other economics students to do their work in Julia. It's also faster in R on Stata, but that's not. It's just speed. It's not that important. Sparse factor models, so the things that you saw where I have to estimate these nonlinear least squares with like factors that control for omitted omitted factor models. So this is a new estimation method that is not available in other languages. And I actually received more emails of people like this package is also in Stata, but so I've coded it in Stata. It's very slow. It doesn't work very well, and so it's basically a Trojan horse. So people ask me questions. Well, my estimation method doesn't work in Stata, and I say yeah, because Stata I couldn't code it properly in Stata. So you should install Julia. You see, and then they'll write back an email saying yeah, it's amazing. So that's just a way to attract people in Julia. Even if it's not, if it's not that popular in economics compared to like the first fixed effect models. And so I wanted to conclude by thanking a lot of people I've met that have helped me on GitHub, Tim Ollie, Tony Kellman, and John Mas-White for his work on like pool data arrays, and other people in other programming languages like Simon Gore and Sergio Correa. I did a lot of work on like sparse linear least squares. And Sami Agarwal is the author of like a nonlinear least squares, like the cirrus solver from Google. And so he helped me a lot to set up my package. Thank you very much.